Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Klaus von Klitzing's 1986 Nobel lecture, titled simply The Quantum Hall Effect, stands as a foundational document in modern condensed matter physics, a work of profound clarity and understated intellectual power. It serves as a personal and historical account of a discovery that fundamentally altered our understanding of quantum mechanics in macroscopic systems and simultaneously revolutionized the field of metrology. This essay provides a systematic, section-by-section evaluation of the internal claims, arguments, and specific evidence presented within that lecture. The analysis will delve into the methodological assertions, the interpretation of the core data, the engagement with theoretical paradoxes, and the far-reaching implications for physical standards as articulated by von Klitzing himself. The objective is to assess the work on its own terms, appreciating the intellectual architecture constructed by its author to explain a phenomenon that was, and remains, a startling manifestation of quantum principles on a tangible scale. It is an exploration of how a meticulously crafted experiment, presented with lucid precision, can reveal a truth about nature so exact and so universal that it becomes a new definition of reality itself. Section 1: The Historical Stage and the Two-Dimensional Electron System. The lecture commences by situating the discovery within its proper historical and conceptual context, a deliberate rhetorical move that frames the quantum Hall effect as a deep extension of established physics. Von Klitzing begins with a respectful nod to Edwin Halsey's 1879 discovery. Presenting the classical Hall effect as the essential precursor, he explains its mechanism. When a current flows through a conductor in a perpendicular magnetic field, a transverse voltage develops, proportional to both the current and the magnetic field strength. His evaluation of this classical foundation is utilitarian. It provides the terms and the basic experimental geometry. The core claim he develops in this section is the unique suitability of a specific technological device, the silicon metal oxide semiconductor field effect transistor, or MOSFET, as the ideal laboratory for exploring this physics in a new regime. He meticulously details the structure of the MOSFET, emphasizing how applying a positive voltage to the gate electrode creates a thin inversion layer at the silicon and silicon dioxide interface. This layer, he argues, confines electrons to a plane, forming what is effectively a two-dimensional electron gas. This claim is central. The genius of using the MOSFET lies in its function. As a capacitor, the carrier density of the two-dimensional system becomes directly and precisely proportional to the gate voltage. This provides the experimentalist with a continuously tunable parameter, an essential capability for methodically mapping out the system's behavior. His argument here is one of experimental elegance and control, asserting that this semiconductor device, a product of the microelectronics industry, offers an unprecedented window into the quantum world of electrons under extreme conditions. The evaluation of his choice is that it was transformative, moving the study of quantum transport from esoteric, specially grown crystals to a ubiquitous and well-understood piece of technology. Section 2: The Experimental Conditions and the Emergence of Quantum Phenomena. This portion of the lecture transitions from the conceptual framework to the stark physical realities of the experiment. Von Klitzing presents his claims about the necessary environmental conditions with the quiet authority of an experimental master. The required ingredients are twofold: extremely low temperatures, approaching absolute zero, and immensely strong magnetic fields. He describes the use of liquid helium to cool the silicon MOSFET and the deployment of superconducting magnets to generate fields millions of times stronger than the Earth's. The claim here is methodological. These extreme conditions are what force the quantum mechanical nature of the electrons to become dominant. At high temperatures, thermal energy smears out the discrete quantum states into a continuum, yielding the familiar linear response of the classical Hall effect. By systematically lowering the temperature, he asserts, this thermal noise is suppressed, allowing the underlying quantum structure to emerge. His argument rests on the concept of Landau quantization. He explains that in a strong magnetic field, the allowed energy states for electrons in a two-dimensional gas coalesce into a set of discrete, massively degenerate levels known as Landau levels. The spacing between these levels is proportional to the magnetic field's strength. It is a powerful claim that the entire macroscopic behavior of the device, its electrical resistance, will become a direct probe of this microscopic quantum energy spectrum. The evaluation of the section's argument is that it successfully bridges the gap between abstract quantum theory and concrete experimental procedure. He makes it clear that the experiment is a process of purification, stripping away the classical world's thermal chaos to reveal the pristine, quantized reality beneath. The lucidity of his explanation for why low temperatures and high fields are essential tools, a means to an end, or hallmark of the Lever's persuasive section 3. The central discovery and the inexplicable plateaus. Here, von Klitzing presents the heart of his discovery, the raw data that signalled a profound departure from all prior understanding. The central claim of the entire work is presented through a single, iconic graph plot of the Hall resistance and the longitudinal resistance as a function of the gate voltage at a fixed, high magnetic field, instead of the smooth, linear increase in Hall resistance predicted by classical physics. The data reveals a series of perfectly flat and horizontal plateaus. Simultaneously, whenever the Hall resistance is on one of these plateaus, the longitudinal resistance, which measures energy dissipation, drops precipitously to zero. The claim is monumental. The values of the Hall resistance on these plateaus are not arbitrary. They are quantized, adhering to the formula where the Hall resistance equals the ratio of the Planck constant to the product of an integer and the square of the elementary charge. This integer, the filling factor, corresponds to the number of fully occupied Landau levels. The argument presented is one of unimpeachable empirical fact. The data is the argument. He emphasizes the shocking precision of this quantization. The plateaus are flat to a degree that defies intuition, suggesting a mechanism of perfect, dissipationless current flow. Furthermore, he makes the powerful assertion of universality. This quantized value is entirely independent of the microscopic details of the specific silicon MOSFET used. It is unaffected by the sample's geometry, its material purity, or its dimensions. It depends only on fundamental constants of nature. The evaluation of this section is that it represents a masterclass in scientific revelation. Von Klitzing lets the data speak for itself, underscoring the strangeness of the observation with a calm, factual presentation that makes the discovery all the more impactful. The existence of these plateaus was a complete surprise, and his lecture captures the intellectual shock of their appearance. Section 4. The paradox of perfection and the role of impurities. Having presented the stunningly perfect quantization, von Klitzing confronts the central theoretical paradox raised by his own data. An ideal, perfectly clean two-dimensional electron system, according to the simple theory of Landau levels, would only show the quantized Hall resistance at discrete, singular points of gate voltage. It could never produce the broad, stable plateaus observed in the real, imperfect sample. The crucial claim in this part of the lecture is both subtle and profound. The existence of the plateaus is a direct consequence of the material's inherent disorder. Impurities, defects, and potential fluctuations, which one would intuitively expect to disrupt a delicate quantum effect, are in fact essential for its stability. This argument hinges on the concept of localized states. In a real sample, the disorder creates a landscape of potential wells that can trap electrons. These localized states exist in the energy gaps between the pristine Landau levels. As the gate voltage is varied, the Fermi level, which represents the highest energy of the electrons, moves through these states. When the Fermi level lies within a region of localized states, those electrons are immobilized and do not participate in the electrical transport. The current is carried only by the electrons in the extended states associated with the center of the Landau levels. This, he argues, is the key. The Hall resistance remains perfectly quantized and locked to its value as long as the Fermi level is traversing the sea of localized states, which explains the width of the plateaus. The simultaneous drop in longitudinal resistance to zero is explained because the mobile electrons see no available empty states to scatter into, and there is no dissipation. The evaluation of this argument is that it demonstrates remarkable physical intuition, while a full theoretical proof would come later from others like Robert Laughlin. Von Klitzing correctly identified the essential physical mechanism. It is a beautiful irony he presents. A celebrated perfection of the quantum Hall effect is born from the practical imperfection of the material world. Section 5 Metrological Consequences and the Von Klitzing Constant. The final substantive section of the lecture pivots from fundamental physics to profound practical application. Having established the universal and precise nature of the quantization, Von Klitzing makes his most audacious claim regarding its utility. He asserts that the quantum Hall effect provides a new and superior representation of the ohm, the fundamental unit of electrical resistance, the quantity representing the ratio of the Planck constant to the square of the elementary charge, now known as the Von Klitzing constant, has a value of approximately 25,813.8 ohms. Because this value is determined solely by fundamental constants of nature, he argues it constitutes a reproducible and invariant standard of resistance, available to any laboratory equipped to perform the experiment. This claim directly challenges the existing metrological framework, which relied on physical artifacts, typically wire-wound resistors maintained in national standards laboratories. Such artifacts are subject to drift over time and variations in environmental conditions. The argument is one of ultimate stability and accessibility. A standard based on a law of physics is inherently more stable than any human-made object. He presents evidence of interlaboratory comparisons, showing remarkable agreement in measurements of the von Klitzing constant performed worldwide, solidifying the claim of its universality. The evaluation of this proposition is that it was entirely correct and its impact has been immense. Von Klitzing's discovery provided metrology with its first quantum standard of resistance, fundamentally changing the way electrical units were maintained and disseminated. His lecture effectively laid the groundwork for the 2019 redefinition of the C-base units, where the Planck constant was assigned a fixed numerical value, thereby defining the kilogram, and by extension, electrical units like the ohm, in terms of fundamental physics. This section showcases his foresight in recognizing that his discovery was a bridge between the microscopic quantum realm and the macroscopic world of engineering and commerce. In conclusion, Klaus von Klitzing's 1986 Nobel lecture is a model of scientific discourse, presenting a revolutionary discovery with a compelling blend of historical context, experimental detail, and insightful analysis. The internal claims of the lecture, evaluated section by section, build a powerful and coherent case. He begins by establishing the ideal experimental system in the silicon MOSFET, then details the extreme conditions necessary to reveal its quantum soul. His presentation, the quantized Hall-Plated element of pure empirical revelation, a direct confrontation with Lou Lauren, his intuitive and correct identification of the paradoxical role of disorder in stabilizing the effect showcases a deep physical understanding that went beyond the immediate data. Finally, his claim for the effect's metrological significance proved to be prophetic, fundamentally reshaping the science of measurement. The lecture's enduring power comes from its narrative clarity and its author's ability to explain not only what he found, but why it mattered. Von Klitzing crafted an account that is both a personal story of discovery and a universal statement about the deep, quantized structure of our world. The work stands as a testament to the power of meticulous experiment to uncover truths of astonishing precision and profound consequence, forever linking a fundamental constant of nature to the name of its observer.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, Please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.